This is lecture 4 of our course EEE 4705. In this lecture, we will solely focus on input-output ports of 8051 microcontroller, how we can program those, use those in different applications. We will try to understand using assembly language. And we basically followed chapter 4 of Majidi for this particular lecture, and also some of the contents were taken from the book from Subrata Ghoshal as well. So let us start. I think previously in this semester we never actually looked at the pin diagram of 8051 in detail, so in this lecture we will do that. In this particular package of 8051, we can see that this is a dual inline package with 40 pins, right? And out of those 40 pins, 32 pins are basically dedicated for input output pins. Okay, so what we have is we have 4 ports, and these are called P0, P1, P2 and P3. Each of the ports have 8 pins. So you will see that, like if I talk about just port 0, you see port 0 is actually these ones starting from 39 to 32. So these 8 are basically port 0. So in this way you will see we have 32 pins here, which are basically input output pins. So they are called input output ports because they can be used as input ports as well as output ports. But one of the thing is, I think you have already seen this, learned this in your lab, that whenever we want to use any port as input, that is, we will try to get data from outside, from that pin or from that port. We have to first of all write a logic high to that pin or that port. After that we can actually use that as input. So why that happens, internal mechanism and the structure, these things we will try to discuss in this lecture, and we will understand why we need that, why we need to actually write logic high before we can make any port or any pin input or behave as input. And some of the things you will observe here is, like for port 0, you will see that if I want to use port 0, I have to, or we have to connect external pull-up resistors. So why we do that, that will also be discussed in detail in this lecture. But you will see that for the other 3 ports, port 1, port 2 or port 3, these things are not necessary. Internal pull-ups are already built inside of the chip, so that we don't have to externally connect any pull-up resistor for it to use as input or output port. So that is one of the things. So one by one, let us try to look at each of the ports. So you will see for most of the ports there is a basic responsibility or purpose, that is we can use that as input or output port, right? But with that, you will see some of the ports also have some additional purpose. Like for example, if I talk about just port 0, which is pins 32 to 39, so from here to here, these are the actually port 0 pins. We have 8 different pins, and these pins are basically called using this kind of notations. So P 0.0, so this is that first pin, right? This one. Then P 0.1. In this way we address each of the pins of a port, right? Now in some of the cases, we have to connect external ROM with microcontroller. For example, if we talk about 8031, that was called ROM-less microcontroller, ROM-less 8051. So for that, obviously we have to externally connect one ROM so that we can use that microcontroller. So in those cases, the address bus and data bus has to be built through some mechanism, right? That mechanism is basically done using this kind of ports. So we know that for address we need 16 different pins or 16 bits, because our addresses are of 16 bits, and for data is 8 bit. We know that. So for those cases you will see port 0 basically helps to that. So port 0, the pins can act as both data bus as well as address bus. So for address, just the lower 8 bit of the address can be utilized using this port, and also the data that will be coming from the ROM to the 8051, that can also be governed by this port 0. It is only for the case whenever we are trying to interface an external ROM with our microcontroller, in that case, right? And you will see I can just add with that, like port 2 also helps with that. Like we know that 16-bit address and 8-bit data, this connection needs to be given with the external ROM with our 8051. So the higher 8-bit address is actually provided by the port 2, and the lower 8-bit address is provided by or port 0. And also with that, it can also provide the path for data as well, the 8-bit data, so it can kind of like multiplex. So because of that reason, because it has to multiplex between data and address, so kind of like bi-directional data path. So to make that happen, it has to have some special architecture. So that's why as you have seen in the previous page, we had to say like port 0 doesn't have any internal pull-ups. That's why to use that as input or output port, we have to connect external pull-up register. So this is one of the reasons. So all of the things I'm talking about here in detail we will understand later on when we actually look at the internal architecture of these ports or pins. Okay, so if I talk about port 1, it doesn't have any kind of additional functions it has to fulfill. So as you can see here, from pin 1 to pin 8. But for port 2, you already know it has to serve the purpose of higher 8-bit address if external ROMs are connected for that case. Now let us look at port 3. So port 3 is basically from 10 to 17, right? So from here to here, these are the 8 pins we are talking about, and these are very special pins because all of the pins have some special functions with the general function we need to have, input and output pin. So as you can see, like 3.0 and 3.1, these are for serial communication, RxD and TxD, these are used, and 3.2 and 3.3, these are interrupt pins. So all of the things we are talking about here, like serial communication, then interrupt, all of them will be discussed later on in the future chapters in detail. Pin 3.4 and 3.5, these are basically timers, can serve as timer, and pin 3.6 and 3.7, this is read-write pins for the case whenever we are trying to connect an external ROM with our 8051. In those cases, it will act as the read-write pin. Okay, so another thing you have to understand, like you see, this one is active low, this one is active low, and also these two are active low. For now, we don't have to understand anything about these functionalities of these pins. We can skip those because we will see that for each of the topics we're talking about here, we will have dedicated chapters to understand how they actually work. Now we have talked about the 32 pins of the total 40 pins of 8051. Then we have some other pins, like you can see this one, VCC and ground. Obviously you know that we have to provide 5 volt and 0 volt to these two pins so that this IC can work, right? And there is another one we will discuss in detail about this one, RST or reset pin, in the next page. Then we have these two crystal 1 and 2, pin 18 and 19. These are basically used to connect the crystal oscillator to give the frequency of our microcontroller. And then we have these 3 pins, EA, this one and this one. For now we don't have to worry about these 3 pins, we can just skip those. But now let us look in detail about reset pin, so which is pin 9 of our microcontroller. So whenever we say resetting our microcontroller, basically what we mean is our microcontroller goes into its initial condition, right? So some of the major changes that happens whenever we reset our microcontroller are these 4. So we know program counter will become 0000, the initial value. Then stack pointer will be initialized to 078, so that means our stack will start from 08, right? And register bank 0 is selected, and also all 4 ports we have, they are initialized to FFH, so all of the bits become 1, right? So they are set as input basically whenever we reset our microcontroller. Another thing which is quite important, whenever you are resetting your microcontroller, you have to provide a logic high voltage to that pin. For how much duration? For at least 2 machine cycles, or we can also say 24 oscillator periods, 24 clock pulses, right? Because you know for our 8051 microcontroller, 12 clock pulses equal to 1 machine cycle. That's why we need to have this amount of time at minimum, and we have to give 5 volt to that pin for that duration at least, so that our microcontroller is properly reset. Now, how to actually build that reset circuit? So you will see we have 2 possibilities here. Even in your lab, if you look at the trainer board, you will see that in this way actually these circuits are built, the reset circuit on our trainer board. So one of the possibilities is power on reset circuit, another one is manual reset circuit. So first of all, let us understand power on reset circuit. So as we said, we have to have at minimum 24 oscillator periods of logic high signal sent at this pin for our microcontroller to be reset, right? So basically what happens whenever we actually power on our microcontroller, at that moment that reset will happen. That's why it's called power on reset circuit. So whenever we power on this microcontroller, what basically happens? Obviously we are going to get this 5 volt here, this 5 volt here, and for some duration we are going to get 5 volt to this pin, and afterwards we are going to see that the voltage we are getting at this pin is 0. So how that happens? To understand that, let us again try to recall our knowledge of capacitors. Okay, so how it behaves with DC circuit. So let's say we have a DC voltage source like that, and we have a switch here, and this is one capacitor here. Okay, now if we connect this switch, and let's say this is 5 volt, and what we are trying to do, we are trying to measure the voltage across the capacitor. Let us call that what, VC maybe, right? So whenever you have started or connected this switch, so obviously this capacitor will start to get charged. So initially the charge was 0 between the plates. So afterwards we will see that charges will flow through this path, and it will get charged and charged and charged, and at the final condition, whenever we reach the equilibrium, VC will be equal to 5 volt, and at that moment no current will flow in this path, and capacitor is fully charged, and this particular capacitor can be considered as open, but the voltage difference between these two plates will be 5 volt, right? Whenever we learned about these things, if you remember, we had an equation like that to calculate the voltage across capacitor. Okay, so this was the equation, right? This V is basically the supply voltage, so let us call that maybe Vs. So Vs is this one. So in this particular equation, which is giving us the voltage across this capacitor, if you take t is equal to 0, then what will happen? We know e to the power 0 is equal to 1, so 1 minus 1 equal to 0. So that means initially the voltage we are going to get across this capacitor will be 0. So you can consider these 2 points A and B, let us call that A and B, shorted, because the voltage difference between these 2 points is 0. So initially whenever we start our microcontroller, exactly the same thing will happen between this point and this point. Okay, so let us call that A and B, and we are going to see that there is no voltage difference between these 2 points. That means this can be considered as shorted, right? So that means we are going to directly get the 5 volt through this path to our reset pin. So we can calculate the value of this capacitor value and also the resistor value, so that the time is long enough so that we get for at least 2 machine cycles the logic high we need for this reset pin. Understand? So this is how we are going to design this power on reset circuit. Okay, so initially we will see that this path can be considered as shorted, and for some duration that 5 volt will be going through this reset pin. That duration should be at least 2 machine cycles. Afterwards it can decay, so that means it will get charged up and this path will be opened, and we are not going to get the 5 volt we were getting initially, and afterwards reset happened, and now our microcontroller can be used. Okay, another thing you can do, which is manual reset circuit. So what we have done, we have just connected one push button here, so that whenever we press the button, directly this 5 volt will be going through the reset pin and our microcontroller will get reset. Okay, so now very important topic for this lecture, we will try to understand internally how the pins of microcontroller ports or 8051 ports are built, and how this can be used, these pins can be used as output or input. Okay, so let us first start with output. So this is just one of the pins, the architecture or the structure of one of the pins of our ports. So these ports are basically can be port 1, port 2 or port 3, because for port 0 the architecture is slightly different, so we will not think about that for now. So you can consider this particular circuit or this structure a pin of either port 1, port 2 or port 3, no problem, they are identical. Okay, and basically what happens whenever you write anything to the port, like let's say if I write something like this, set B so if I give this command, what basically happening is we are going to get logic 1 at this point from the internal CPU bus. You are going to get that, and one by one try to understand each of the components of this circuit. So this one is just a D latch. So whatever you give through this line, 1 or 0, if you enable the latch, so this is level triggered. So basically if you have something like this kind of pulse, let's say, so this is 0 and this is 1. So whenever you have 1 at this moment, whatever you have at D will be latched onto Q, and that will be stored basically onto our D latch. So we are going to permanently get the value at this pin, even if afterwards I remove the signal here. That's how latches work, right? And this one, I think you already know about this one. This is called tri-state buffer. You learned that in your third semester maybe. So tri-state buffer is basically works in the mechanism that if you have 1 here at the input, let's say 1 or 0, nothing will happen at the output as long as you don't give any kind of enable signal through this particular pin. And whenever you give 1 here, which will enable this buffer, and whatever you have here, 1 or 0, that will be passed on to this output, right? One of the benefits of these buffers is, it can isolate the input side from the output side. So if there is any kind of problem like high amount of current is flowing, any surge is happening at the input, that will not affect the output. That is one of the benefits of this kind of buffers, right? So we have two buffers here. One of them is called read pin, another one is read latch. Don't worry about this for now, we will properly understand everything, but just try to understand all of the components we have for this circuit. Then let us look at this particular MOSFET here, which is connected with the Q bar of our latch, D latch, right? So this is the gate, this is the drain, and this is the source, right? Source is connected with the ground, but the drain is connected to the VCC through a load. So this can be considered as just a simple resistor, like pull-up resistor. Pull-up resistor, basically what it does, it is a resistor that connects with the 5 volt, so that if needed we can get the 5 volt for digital circuits, right? So this kind of acts like a pull-up resistor, internal pull-up resistor. We will properly understand what purpose it has in our circuit. Okay, so now let us try to understand the working principle whenever we are giving a logic 1 through this internal CPU bus using this command, right? Whenever we give this command and we are trying to use this particular pin, which is P1.x, it can be 1.0, 1.1, 1.2, whatever, we are trying to output a value of logic 1 with this pin. So if I give this command, we are going to get 1 here from the internal CPU bus, and also at the same time we will have a latch signal coming here at the clock, so that the signal goes to this Q. So at the output we are going to get 1, and if this is 1, Q bar should be 0. So if this is 0, that means we are giving a low signal to the gate of our MOSFET, right? So that will not enable our MOSFET, and this path will not be complete, right? This is open circuit right now because we don't have enough gate signal to turn this path on, right? So this is open circuit, can be considered. And because of that, what will happen at the output, this is the output pin basically, right? So the pin here, we are going to get the VCC signal, or 5 volt if you can say. This signal will be going here because the voltage drop in this path we will consider as very low, so that essentially we are getting the 5 volt here. So you understand now, because of that, because of this pull up resistor, from the VCC we are getting 5 volt, which is what we needed. If we give this signal, what we want at the output or at the end of the pin should output 5 volt or logic high. So that is happening. Now if I write CLR P1.x, if I do that, then obviously we are going to see that this value is 0 we are going to get. Because of that, this value will be 0 and Q bar will be what? 1, right? If this is 1, we have good enough signal to turn this path on for this MOSFET. So this path will be shorted, and as a result, because this path is connected to the ground, at the output we are going to get logic 0, right? Which is what we wanted. We wanted to output or write logic 0 to this particular pin. So in this way, pins of 8051 ports acts as output. Now we will try to understand how we can use this pin as input. So as you know, we previously discussed that to use any port or any pin as input, first of all we have to write a logic high to that port or that pin. Afterwards we can use that as input. So why is that? So for this particular pin, let us first provide logic high, write logic high to the pin. So for that, what we have to do, let's say we write set B P1.x, which will give us logic 1 here. We are going to give proper signal here in the clock, so that this signal logic 1 is latched onto Q. So we are going to get 1 here, and because of that we are going to get 0 here. Q bar will be 0, so which will be basically turning off this MOSFET. So this path is essentially off, right? So if this path is essentially off, now we can connect this pin with any external sources we have to provide input. It can be 5 volt, 0 volt, whatever. Let's say, for example, first let us give an example. Let's say we give logic 1 here. So what will happen? This logic 1 will go through this path and it will reach here. Nothing will go in this path because this path is opened, and because already this is VCC and we are providing logic 1 which is almost equal to VCC. So that means there will be no conflict here, and the signal will be going through this path, right? And then we can write something like this: MOV C P 1.x. So this is just carry bit of our PSW register. So what we will try to do, or what we are trying to do here, is whatever signal or value we are getting from the pin, this pin, that we want to store onto carry, right? So if we give this command, what will happen? This read pin signal will be high, so that will be activated and will activate this tri-state buffer. Because of that, this signal will go through this path and come here, the same place as before, right? And because this is next clock pulse, so previous logic 1 will not interfere with this one. In this way, sequentially, any kind of digital logic device works, so we don't have to worry about that. But whatever signal was provided from externally as input, that will come here through this path and go through the internal bus like that, and that will be stored onto the carry bit of our CPU, right, of our PSW register. So in this way, that will be stored. Same thing can be said for if we have given logic 0 externally, like if this is 0, then what will happen? This path is still off, so nothing will come from here. And because we have a pull-up resistor here, this 5 volt or VCC and this logic 0 will not cause any issue because of this resistor. So very minuscule amount of voltage will be dropped here, that is true, but that will not affect because of this tri-state buffer. So that current will flow through this path, but because we know tri-state buffer will isolate the output from the input, because of that, if this command is given, read pin will be activated, activate this tri-state buffer, and that 0 signal will come through this path and come to the internal CPU bus, go to our CPU, and that will be stored onto our carry bit, right? So in this way, this thing works. So you understand. Now let us discuss about the issues or problems that can happen in this condition. Like, one of the things we have understood, obviously we have to provide or give logic high to our pin first if we want to use that pin as input. If any input is going to be coming here, then first of all we have to give logic 1 using this kind of command, right? So what will happen if I give 0 signal? If I do something like that, like before doing that, if I do something like this, what issue can actually happen in this particular thing? Let us look at that. So if that happens, you see we have given actually 0 here. After writing to latch, it will come here at Q, and Q bar will be 1. That will turn on our MOSFET, and this path will be essentially shorted to the ground. And at that condition, if you have any signal, like in this particular signal, what we have a switch which can be turned to 5 volt or VCC or to ground, and currently it is actually connected to 5 volt or VCC. So that signal will go through this path, go through here, because this path is shorted without any resistance. Huge amount of current will flow into our 8051, and that will damage this MOSFET. Our device will be damaged. So this is one of the issues we have to be very careful about. So whenever we are trying to use any port or any pin as input, we can never write 0 to that particular pin. That will cause this issue, right? So how can we actually resolve that? With the help of hardwares, hardware circuits. How can we resolve that? So that if accidentally we have given 0 signal to our pin before giving external inputs, and this kind of issue if happens, how can we avoid those using a hardware circuit? So one of the examples is this. So what we can do, we can connect just a pull-up resistors like that through the 5 volts, so that this switch can be connected here or it can be open. So whenever this is connected, this switch is connected like that, so essentially we are getting ground. And if this is ground, if logic 0 is coming here and this is shorted, no problem is there, because both of them are ground, so no current, not huge amount of current will flow here, so that will not cause any problem, and we are going to get whatever signal we are trying to give here. That will go, right? And for the case of situation when this switch is opened, so we are directly going to get this 5 volt through this resistor that will come here. So obviously there will be some amount of voltage drop here, there will be some current flow here, but because of this resistor here, at least this MOSFET will not get damaged. So we can avoid that mishap using these resistors. Okay, another possibility is that we can also use this kind of push button through the help of ground. In that case, whenever the push button is not pushed, at that moment no signal is coming from here, but we are getting signal from this internal pull-up. So VCC is coming. So whenever we are not pressing this push button, we are assuming that we are sending 5 volt or high logic high. That logic high will go through here and will be latched onto internal CPU bus with the help of this tri-state buffer, right? And whenever you press this push button, directly this ground will come here. But even if this is shorted path, both of them are ground, so no issue will happen, and we are going to get the logic 0 signal through our tri-state buffer to the internal CPU bus. So basically, using these mechanisms, you can at least avoid the damage of our MOSFET. So these are some of the approaches we can actually use. So far we have talked about the pins of port 1, port 2, port 3. These are identical pins. Now we will talk about pins of port 0, which is slightly different than the previous ones in the fact that it has no internal pull-up. You see, this portion is actually disconnected. So we use this term called open drain, right? So open drain basically means in this MOSFET, you see, this is source, this is gate, and this is drain, and drain is not connected with anything. This is open. So that's why open drain. And if you want to use this port or this pin as input or output, we have to deliberately externally connect pull-up resistors to make it work. So something like this, we will use a resistor of 10K and through VCC and connect it with this drain. Basically we will see this pin coming from our 8051. Outside we are going to give this kind of connection, something like this. Okay, so this is the whole port 0. So what we do, all the pins we have, we just connect 10K resistors and connect all of them with VCC. So then we can use this particular port as input or output as we want. Now someone may ask why we have this issue with port 0, why it is not like other pins we have for port 1, port 2 or port 3. We could have used internal pull-ups. The reason is, if you remember, port 0 has a very special responsibility purpose, that is it has to act as both address path and data path for external ROM. If we want to connect external ROM, it has to provide path for both. So it has to be truly bidirectional port basically. So there are two terms called quasi bidirectional and true bidirectional. So all of the circuits we have seen for port 1, port 2 and port 3, these pins are, or these ports are called quasi bidirectional, almost bidirectional but not truly bidirectional, because even if you actually provide one here, which is the prerequisite for it to behave as input pin, then we can get 0 here that will turn off this particular MOSFET and no current will go through this path. So then we can actually use the input signals to come inside of our microcontroller, right? But still you see this thing is here and current can flow from this path to this path. So still we are unable to completely shut down the flow of signal from inside of the microcontroller to outside. So it is not truly bidirectional. So whenever we mean truly bidirectional, whenever one of the direction is giving a signal, signals from other directions will be completely shut off. That is not possible for this particular circuit. And you are going to see whenever we actually go to that chapter to understand how we can connect an external ROM with our 8051, then you will understand the significance of this kind of pins of port 0. For now, let us keep our discussion up to this much, and let us try to understand the code syntaxes in assembly language we can use to use those ports or these pins specifically. Okay, so the first example, we will look at how to use a port as input. So we know from the hardware example that we have to first of all write logic ones to our pins or ports to make it an input port, okay, or input pin. So you see in this example that is done. In this example, because we want to use our port 0 as input, what we have done, we have actually moved FFH to register A, which is all ones, basically all ones, all 8 of them are ones. That value is moved to P0. So now essentially after this line, we can use our port 0 to get any kind of input from outside of the 8051, right? So now in this line, it can look a bit confusing, but what is happening is after you have configured your port as input, now whatever signal that is connected externally with our port 0, that will give us signals, right? 8 different signals, basically ones or zeros. That signal we will try to save that onto our register A. So we are reading the pin, reading port 0. And then we can also do another thing, that is whatever signal we are getting as input onto our port 0, we can actually write that onto port 1, right? So that is what we have done here. We have taken input signal from port 0 and actually write that onto port 1 with the help of register A, right? So we will try to do that over and over again because we have already configured our port 0 as input. So that means this loop will infinitely go on, and always we will try to read the signals we are getting as input on port 0, and we will try to write that onto port 1. So this is just one example. Okay, now let us look at some other examples. So there are different ways to access our ports. Like the most common approach is this one. I think we have seen multiple examples like that. So what we are doing, we are just complementing the bits of our ports with the help of 55H. So 55H and AAH are basically complement of each other in terms of bits. So that is what we are doing. We have moved this value, and then because this value is stored onto register A, we will just move that onto P1. Then we will have some delay. That delay can be written here even though it's not written here. Then again we will move this value, which is the complement of this value, to register A. Then we will write that to P1. In this way we will just complement the bits and take some delay. Very simple to understand code, but this is not that efficient in terms of how we have written it. We can efficiently write it in this way. We don't have to use this register A every time. We can directly write the immediate data onto our ports. That is valid, right? We can call the delay, then again write the complement value to our port, then delay in this way. You can also do another thing. You can use, or you can take the help of this command cpla, which complements all the bits we have in a particular register, right? So what we can do initially, we can start with this value onto our register, then move that value onto our port 1, then take the delay, then complement this value of register A. Then if I short jump here, basically what will happen, this value is already complemented here, that value will be moved on to P1. So in this way, after each loop, the bits of port 1 will be complemented, each of the bits will be complemented. So this is just 3 examples of how we can write the same code in 3 different ways. But one of the things you have to understand, like what we have done here, every time immediate value was stored onto A, then that value was moved on to P1. We don't have to do that. We can directly write any kind of immediate data onto the ports that is valid. Now, one of the most powerful functionality of 8051 microcontroller is we can control each of the bits separately. All of the ports we have, for each of the ports, each of the pins can be controlled separately. So that is very useful, and most of the times we use that in different applications. So these are just some of the examples like that. I think some of them you have already seen from previous lectures. You know what is the statement and what is the function of this kind of instructions. Okay, if you don't understand still, we can look at some examples here. So these are some practical examples, and in the exam there can be questions like the ones we are seeing here. Okay, so look at this one. Create a square wave of 50% duty cycles on bit 0 of port 1. So basically pin 1.0, right? So let us try to solve the first one. Something like this we have to create. So this is called the square pulse. 50% duty cycle means of the total period we have here, 50% of the time we have to give one signal, logic 1, and 50% of the time it should be 0. Okay, so that can be done easily, right? Half of the time should be on, half of the time it should be off. So that can be done like the code we have here. We have deliberately set the P1.0 pin. So this is logic 1, then we are going to call the delay. You have to write the delay subroutine. Even though this is not written here, you have to write the delay. Maybe in the exam there will be written the amount of delay you have to give, like what is the amount of time for each time period of the square wave we have generated. Maybe that will be given. Based on that, you have to calculate the delay, right? Delay subroutine has to be written. So what you said P1.0, then you are going to call the delay, then you are going to clear the bit, again going to call the delay. So you are going to get same amount of delay for logic 1, same amount of delay for logic 0. So 50% duty cycle. Very easy to understand. Another thing you can do, this same code can be written here like this. So what we have done, we are going to just complement that particular. CPL can be used in ports as well as pin. Okay, so here we have used for this particular pin, so P1.0. if I use that, whatever value we have for pin 1.0, that will be complemented. Then we are going to call the delay, which will be written here. Then we are going to short jump here, so come here. So it will just toggle basically from 1 to 0, 1 to 0, but with same amount of delay. So we are going to get 50% duty cycle. Then the next problem, this one, we have 66% duty cycle. So 66% means 2/3 of the time should be on, 1/3 of the time should be off of the total time period of the square wave, right? So basically you can create a delay. You can call the delay twice for on, set B, and for clear you can call the delay once. So in this way you are going to get 66, or basically 66.66, whatever you say, yeah, approximately 66% duty cycle you are going to get here. So easy to understand. These are quite easy examples, right? I'm just going through those because in the book these examples are given, and also in the exam you can find similar kind of problems. Very similar kind of problems will be given in the exam. So let us look at this example from your Majidi book. So here they are saying we have to monitor a particular bit until it becomes high, and whenever it becomes high we have to write a value to port 1 45H. Then we have to do another thing, which is give or send a high to low pulse. So high to low pulse, something like high, then to low pulse, something like this. If this is 1, then this is 0. This kind of signal has to be given to pin 2.3. So what we are going to do, first of all, because we have to monitor the behavior of port pin 1.2, that means we have to configure it as an input pin. So we are going to observe externally what signal is given to that pin. So that's why we are setting this particular pin to high, so that we can configure that to input. Then in this line we are going to monitor. In a loop we will try to observe or monitor the condition of pin 1.2. So jump not bit 1.2. So as long as pin 1.2 is 0, we have to go to this label again. So it will just keep itself in this loop until pin 1.2 becomes high. At that moment what will happen, it can skip this line and go to the next line, which is the execution of the next task we have. So we are going to, if pin 1.2 is high, then we can complete this task. We are going to write this value onto port 0, and we are going to give a high to low pulse to pin 2.3. So we will first set B, then clear it. So that will give us first a high pulse, then a low pulse. So high to low pulse basically. Understand? Then next example here. This example, they are saying that we have pin 2.3 as an input and represents the condition of an oven. Okay, if it goes high, it means that the oven is hot. So we have to monitor and look for the moment whenever this pin basically becomes high. So first of all, we have to configure that to input. This pin has to be configured to input. Monitor the bit continuously. Whenever it goes high, send a high to low pulse to port 1.5 to turn on a buzzer, right? So yeah, even though it's not written here, we have to write it here. We be very careful. Like you're talking about pin 2.3 and we have to use that as input. So first of all, you have to write set B pin 2.3. First of all, you have to write set B pin 2.3. Here you have to write set B pin 2.3. Now it's configured as input. Now we are going to monitor the condition of pin 2.3. So if this is low, that means we are going to just be in this particular line in a loop, and then whenever this pin becomes high, we can skip that and go to the next line. So you see set B then clear, that means high to low pulse will be given to this particular pin, and then after doing that will turn on the buzzer. Basically we can again move on to our first line to again monitor what is happening to our input, right? So yeah, next we have another example. So here a switch is connected to pin 1.7. We have to check the status of the switch and perform the following. If switch is 0, that means we have to send a ASCII letter n, ASCII value n to port 2. If switch is 1, then we have to write ASCII letter y to pin 2. So not that difficult here also, because we are monitoring this particular pin. What we have done, we have first of all write 1 to pin 1.7, it is configured as input, then we are going to monitor the condition. So if this is 1, so jump if bit means if this particular pin gets an input signal of 1, we are going to get to over, and over means here we are going to do whatever is asked. So we are going to move ASCII value y to port 2. So that is done. You see, in this way you can actually write a ASCII value using this kind of quotation and then hashtag. You can actually write a ASCII value to a particular port. That can be done. Then after doing that, you are going to go to your initial moment here again you are going to monitor the condition of our pin 1.7, and if if this is not 1, let's say switch is pressed such that SW is 0, then what we are going to do, we are not going to go to over, we are going to go to this next line, it can skip, and we are going to write the ASCII value n to our port 2. So in this way again we are going to go to the label again. So in this way this particular code will work continuously in an infinite loop. So 4.6 again the same problem, but here what they have said is use the carry flag to check the switch status. So instead of what we have done in the previous case, we have to use carry flag. So not that difficult. So again we have written logic 1 to our pin to make it input pin. Then we are going to move whatever signal we have that we are getting as input on pin 1.7, that will be moved to carry bit, and after that we are going to use this conditional statement that if carry has happened, then we are going to jump to the label over, right? So if we are going to get a 1, if this signal is 1, then we have to go to over, and the command is basically we have to write y to p2, right? And if this doesn't happen, if carry is 0, then we can skip this line, we can move on to the next line, which is basically writing n to p2. So I think you can understand, pretty simple to understand. Okay, I think this is the last one. Yeah, so in this example what they have done, they are saying that a switch is connected to the pin 1.0 and an LED to pin 2.7. so write a program to get the status of the switch and send it to LED. So whenever switch is pressed, LED should be on, when switch is not pressed, LED should be turned off, right? So in this way, so we are monitoring the condition of one of the pins and trying to manipulate another pin to turn on and off the LED, right? So here you see, first of all we have configured our pin, this pin as input. Now we are going to check the condition. So in this particular line, what we are doing, in this pin as input, whatever signal we are getting, that will be stored onto carry flag, okay, and that carry flag will be moved on to this particular pin, which is the output pin, basically to turn on or off the LED, right? So that will be done. So in this way continuously we are again going to go to this line with the help of short jump, and every time it will check the condition of pin 1.0 and change the condition of pin 2.7. but you can never write something like move pin 2.7 comma pin 1.0. so you cannot move value from pin to pin, but port to port that is allowed, okay? So like in one of the examples, I think in the first example we had seen that we had to take the help of register A to get some input value of port 1 and send that to port 2. That can be done using just this one command, okay? Okay, so whatever we have talked about so far may seem easy, but now it will get complicated because there are two possibilities whenever we are trying to read from a pin of microcontroller ports. One of the things we have already seen so far, so basically whatever we are sending from the outside to our pin, we are getting as input that is being read through this path, right? Because of this read pin signal which is enabling this tri-state buffer, right, TB1. But you will see we have another tri-state buffer here which is connected with the output of the latch with the Q basically, and we can actually send signal to this read latch so that the signal we are getting at the output of the latch can be going to the input again, right? So that is called reading port latch. So there are assembly instructions such that it will not read the input pin, so it will not read whatever we are sending from here, rather whatever we are getting here. So what are those assembly instructions? Let us look at one example. So one of the example is this one. So ANL P1, A. So for this case, what will happen? First of all, it will activate the read latch of tri-state buffer 2, okay? And obviously we will have something here, you know, from the previous instruction, maybe something stored in our port 1 in this pin. That value will be coming through this path to the internal bus, and that will come to the CPU. So that value and the value we have stored in register A, they will be combined in such a way which is kind of like bitwise AND. So maybe let's say for example P1 is giving a value like this 1010 1100, and in register A we have saved something like 1100 1110. So if you do bitwise AND, you are going to get what? 0, this will be 0, this will be 1 1, this will be 0, this will be 0 again, and this will be 0, and this will be 1. So if both of the bits are 1, only then the output will be 1. So in this way, this will be the resultant value after this instruction execution, right? And basically this result will be written onto the latch again, okay? So that will come to this path. We are going to enable this clock so that particular bit comes here, and that will happen to all the 8 pins of port 1 so that we get the updated value. So in this case we are not reading what is coming from here, from outside of the port as input, rather we are reading what is inside of our latch, right? So basically let's say maybe in the previous instruction we have written something onto our port 1, and that value will be stored on this Q, and we are, whenever we have this command, we will try to read that with the help of this read latch that will be coming here, and that value and the value of register A, these are bitwise ANDed together, and the result again will be written to our port 1. So this is called reading port latch. So we have to be very careful when we are actually reading the input pin and whenever we are reading the port latch. So there are different commands like that. So just reading input port or pin. So you have already seen these kind of instructions. These are basically reading the input port or pin, and in all of the cases, in most of the cases, you will see that the source is actually the port itself. So we are getting some data from the source, and in these cases we are reading the input pin rather than reading the port latch. And also sometimes, like for these cases JNB or JB, we are trying to monitor the condition of a particular bit. This is also reading input pin. We are trying to read the condition of input pin, and based on that we will make decisions, right? Also these things, like we are trying to read the condition of this particular port by looking at externally what is connected with our port, which is giving us the input, and comparing that with register A, and based on that we will make comparison and go to the label. But for the case of the port latch, if we are reading port latch, what we are doing, if you remember from the previous example, first of all we have read the port latch. We have read the port latch by enabling this read latch that has come here and gone to the CPU. We have done some modification. The value we have got at P1 through the help of TB2, and the value stored in A, both of them are bitwise ANDed. So this modification, whatever modified value we have got, this value again was written to the port. So these particular instructions are called read, modify, write instructions. First of all we read from the port latch, then we modify, and then again we write the modified value onto the port. Okay, so these are these kind of examples. So maybe we don't know all of the instructions here, don't worry about that. Maybe in chapter 6 we will learn about all of the instructions here, bitwise AND, bitwise OR, bitwise OR, this kind of things. But you have to understand, in these cases we are actually looking at the port latch rather than external data that is coming through the input pin. Okay, that's all for this lecture. Thank you.